Welcome back. In this module, we address the lifeline of business resilience: data backup, storage, and restoration. When all other controls fail, whether due to a cyber attack, hardware meltdown, or natural disaster, your backup strategy is the final barrier standing between recovery and total business failure. We will explore the technical strategies, rotation schemes, and resilience architectures like RAID that ensure your data survives the unexpected. Let's start with the big picture. Data resilience is not just about making copies. It is a strategic approach to ensuring your organization's digital heartbeat keeps beating. As we see in Domain 4, this involves three distinct phases: backup, storage, and restoration. Why do we do this? Because threats are everywhere, from a failed hard drive to a sophisticated ransomware attack. If you lose your data, you lose your business. However, you cannot just back up everything randomly. Your strategy must align with the Business Continuity Plan, BCP. If your BIA says you need a system back in 4 hours, your backup strategy cannot take 24 hours to restore. The goal is alignment, matching technical capability with business survival needs. This flowchart visualizes the dependency chain. We start on the left with the Business Impact Analysis, BIA. You cannot build a strategy without knowing what is critical. The BIA defines your recovery targets, specifically RTO and RPO. These targets dictate your backup strategy. If you need low data loss, you back up frequently. This strategy executes the actual data backup, which moves data to secure storage. Ultimately, this storage enables restoration, which supports the final goal: business continuity. Notice how it's a linear dependency. If the BIA is wrong, the restoration will fail to meet business needs. Now, let's get technical with the three main backup types. First, the full backup. This captures everything. It's safe, but slow and hungry for storage space. Next, the incremental backup. This is the speed demon. It only copies what changed since the very last backup, making it fast to run. However, restoration is painful because you need the last full backup, plus every single incremental tape since then. Finally, the differential backup. This captures everything changed since the last full backup. It grows larger throughout the week, but offers a faster restore than incremental because you only need 2 sets, the last full and the last differential. Your choice depends on what hurts more: the time it takes to back up at night, or the time it takes to restore during a disaster. Here we visualize the complexity of restoration. In the top group, full backup restoration R1 is simple. You just use Monday's tape. In the differential strategy, to restore on Wednesday R2, you need Monday's full and Wednesday's differential. Note that Tuesday is ignored. In the incremental strategy at the bottom, look at the connections to restore R3. You need Monday's full, plus Tuesday's incremental, plus Wednesday's incremental. The chain is longer, meaning higher risk and longer recovery time. You have the data, now how do you manage the tapes or disks over time? We use rotation schemes. The standard is grandfather-father-son, GFS. Think of it as a hierarchy. The son is your daily backup, usually an incremental or differential. The father is your weekly full backup. The grandfather is your monthly archive. This ensures you can go back to yesterday, last week, or last year. Another method is Towers of Hanoi, based on a mathematical puzzle, which optimizes media usage for long retention. As an auditor, one of the most frequent findings is a failure to rotate. If the same tape stays in the drive for a month, you have no history, and the tape will wear out. This state diagram tracks the life cycle of backup media in a GFS scheme. The cycle begins with the daily son tapes. At the end of the week, we promote a backup to a weekly father. At the end of the month, a father becomes a monthly grandfather. Crucially, the grandfather moves to off-site archive for permanent storage, while the son and father tapes loop back to be overwritten and reused. This visualizes the balance between retention and media recycling. Where do you put the backups? On-site storage is great for quick fixes like when a user accidentally deletes a file. But if the building burns down, your on-site backups burn with it. This is why off-site storage is mandatory for disaster recovery. A critical concept here is geolocality. If your off-site vault is 5 miles away, a regional flood might destroy both your primary site and your backups. Modern strategies often use electronic vaulting or cloud storage to automate this, removing the risk of lost tapes during transport. However, whether physical or digital, all backups must be encrypted. An auditor must verify that the off-site facility is as secure as your main data center. This diagram shows the 3 storage paths. The primary data center feeds the on-site library for quick operational restores. Simultaneously, it sends data via physical transport to a secure off-site vault or via electronic vaulting to a cloud site. The orange nodes, vault and cloud, are the only paths that enable disaster recovery if the primary center fails. The on-site library is useless in a total facility loss. Backup recovers data. Resilience prevents it from going offline in the first place. The most common technology here is RAID. You must know the levels. RAID 0 stripes data for speed, but offers zero fault tolerance. If one drive fails, you lose everything. Never use RAID 0 for critical systems. RAID 1 mirrors data. It's safe but expensive because you buy 2 drives to store 1 drive's worth of data. RAID 5 uses parity to survive a single drive failure, offering a balance of cost and safety. RAID 10 combines the best of both worlds, but is costly. Remember, RAID protects against hardware failure, not file deletion. RAID is not a backup. This diagram contrasts the RAID levels. RAID 0 shows 2 disks linked, but the dashed red box indicates it is risky no safety net. RAID 1 shows a direct mirror link. Data is identical on both. RAID 5 shows the parity distributed between the disks, which acts as the safety net to rebuild data if one disk dies. All these technologies must serve the business metrics, RTO and RPO. Recovery Time Objective, RTO, is your stopwatch. How long can you be down? If your RTO is 1 hour, you cannot rely on tape restoration. You need disk mirroring or hot sites. Recovery Point Objective, RPO, is your data tolerance. How much work can you lose? If your RPO is 5 minutes, a nightly backup is useless. You need real-time replication. As an auditor, you compare the technical capability against these management targets. If the business demands an RPO of 1 hour, but backups run only once a day, 24 hours, you have found a significant gap. This timeline visualizes the concepts. The timeline moves from left to right. Last backup marks the point of safety. The gap between last backup and disaster strikes represents the RPO, the data you lose. The gap between disaster strikes and system restored is the RTO, the downtime you endure. The goal is to shrink both gaps. Making backups is easy. Restoring them is hard. The golden rule is that a backup provides zero value until you prove you can restore it. Many organizations back up faithfully for years, only to find the tapes are blank when disaster strikes. We verify this through rigorous testing. This ranges from a simple checklist review, paper test, to a simulation, role play. The most effective, but expensive, is the parallel test, where you run the backup system alongside the live system. The riskiest is the cutover, where you actually shut off the main system. Auditors look for validation of restore, not just a log saying the backup finished, but a log saying a test file was successfully recovered. This process loop shows the testing cycle. We execute backup and verify logs, but we must periodically branch to periodic test. Here we perform restoration of actual files. We check data valid. If yes, we get an audit pass. If no, we must remediate immediately. Simply looping back from verify log without testing restoration creates a false sense of security. Finally, how do we audit this? Your objective is to verify availability and integrity. First, review the documentation. Does the disaster recovery plan match the BIOS RTO/RPO targets? Second, inspect the offsite storage. Go there physically. Is it secure? Does the inventory list match the tapes actually on the shelf? Third, review test results. Don't just look for success labels. Look for how they handled failures. Did they fix the root cause? Finally, check security. Are the tapes encrypted? Who has the keys? If the backup administrator leaves, are the keys changed? Your audit report will highlight gaps between the plan and the reality. This is the auditor's roadmap. Start by reviewing the requirements, BIA. Then inspect the physical reality, storage. Then check the historical performance, test logs. Finally, verify the controls, encryption. If any step reveals a gap, issue a finding. Only if all pass is the control deemed effective.